Hello, I am Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Knowledge Park 3, Greater Noida. The subject that I teach in this semester for BTech final year student is Optoelectronics and Optical Communication System. And the topic that I discussed in this lecture is Semiconductor LED and Photoemission process. LED means light emitting diode, and this is the optical source and process of photo emission. Well, light emitting diode, it is a semiconductor diode. It's a semiconductor device. Semiconductor device means, it's a diode, basically a diode. And you all familiar with that. When diode is concerned, we have anode, we have cathode, right? And what is the specialty of this diode if you compare with a general diode? The special thing about this light emitting diode is that when the current is flowing across it, it emits light. Light. Okay, so these LEDs, light emitting diodes, are available in the market in different colors, maybe red, green, blue. So in this picture, if you look at that, we have a red color LED, and this LEDs emit light when current is passed through it, right? So basically it is a diode, it's a semiconductor diode, and that diode is a semiconductor device that emits incoherent light. Incoherent light means, incoherent light means because light means that all the photons, because light is composed of photons, all the photons are not in same directions. So this is incoherent light. Through spontaneous emission. Spontaneous emission means electroluminescence, means when electron and hole are recombined together to give a photon, and this is the spontaneous emission. Emission here is term used to emit of light. So emission means emission of light. So when a current is passed through it. So what is LED? So LED or light emitting diode is a semiconductor device that emits incoherent light through spontaneous emission when a current is passed through it. So typically LEDs for the 850 nanometer regions are fabricated using gallium arsenide and aluminum gallium arsenide, and LED for 1300 nanometer and 1550 nanometer regions are fabricated using indium gallium arsenic phosphide or indium phosphide. So the basic LED types used for fiber optic communication system are, so basically there are 3 or 4 types of LEDs that we used in optical communication, and the name of these LEDs are: number 1, surface emitting LED, in short SLED, or edge emitting LED, in short you say ELED, and superluminance or supraluminescent diode LED, right? So LED performance difference helps link designers decide which device is appropriate for the intended application. Means we have various types of LEDs are available in the market, so the engineer decide which LED is suitable for which purpose. So for example, for a short distance, means 0 to 3 kilometer, low data rate fiber optic system, we used SLED, surface LEDs and edge LEDs are used. So depending upon the requirement, we used different LEDs, right? So this is the meaning. So typically, surface LEDs operate efficiently for bit rates up to 250 megabits per second. So this is the speed of that we get from these surface LEDs, 250 Mbps. So because surface LEDs emit light over a wide range, they are almost exclusively used in multi-mode systems. And for medium distance, medium data rate system, edge LEDs are preferred. ELEDs are preferred. And ELEDs means edge LEDs may be modulated at rate of 400 Mbps rather than 250 Mbps in case of SLED. So edge LEDs may be used for both single mode and multi-mode fiber system. And both LEDs are used in long distance high data rate system. So both diodes designed to operate in the super luminance mode. Now we focus on the term photoemission. Photoemission, and that process, that phenomena come when we use these LEDs. Process of photoemission, phenomena of photoemission. And how we get this photoemission process, photoemission phenomena. We get photoemission when an electron and hole recombine in a suitable condition in the depletion region. They may emit light of certain energy. Means in diode, what's happened? Electrons from N region, holes from P region are reached to middle of the region that we call as a depletion region, where they recombine together. When they recombine in the depletion region, which is the middle region of the diode, then certain amount of energy is emitted from that depletion region, right? And that energy that is released in depletion region is equal to the forbidden energy gap of the semiconductor material used to fabricate the PN junction. The meaning is that the material that you use for the fabrication of PN junction, each material has its own forbidden energy gap. So if you manufacture this particular LED or PN junction diode of particular material, then we have a particular forbidden energy gap. So when the electron and hole are recombined in that particular material, the energy is released. That energy is equal to the forbidden energy gap of the material that is used to fabricate this PN junction. So what is photoemission? Photoemission means carrier recombination may occur. Carrier recombination may occur means holes and electrons. So carrier recombination may occur at any place in the whole of PN junction structure, although light is emitted from the carrier recombination site close to the junction. So when the electron hole basically recombine together near about depletion region, so the light that you get from LED is near the depletion region, because the mostly recombination occur at depletion region. So most of the light that is coming from LED is coming from this depletion region, which is somewhere middle of this LED. Now in that category, we have two types of category of LED. One is direct bandgap semiconductor LEDs or indirect bandgap semiconductors. So first we focus on direct bandgap semiconductor. The most suitable material for the emission of light are the direct bandgap semiconductors. So we prefer direct bandgap semiconductor rather than indirect. The reason is, you can understand the reason while listening this particular lecture. At the end, you can understand why we use direct bandgap semiconductor rather than indirect. I can say that because direct bandgap semiconductor, you get quick emission of light. There is no delay in that. What is the reason behind that? That we have to understand in that. So in this particular semiconductor, direct bandgap semiconductor, the electrons at the bottom of the conduction band and holes at the top of the valence band on either side of the forbidden energy gap have the same value of momentum. Means electrons in the electrons in the conduction band and holes in the valence band are at the same momentum. Look at this picture. The number of electrons are there. This particular is conduction band, and holes are there. This is valence band. So and these have on the same energy, same momentum. Actually, this is momentum. K is momentum. This is energy. So means both holes and electrons have have same momentum, right? So this is the meaning. And indirect semiconductor, you know, electrons are found there and holes are found there, but they are not at the same momentum. Look at the momentum. So for that, for the recombination, what's happened? These electrons should lose certain momentum. When they lose certain momentum, they come to that side and recombinations take place. So the recombination in indirect bandgap semiconductor required more time rather than direct bandgap semiconductor. So you get quick light coming from direct bandgap semiconductor rather than indirect bandgap semiconductor, because in indirect bandgap semiconductor, electron and holes are not at the same momentum. Try to understand that with the same figure. So that figure shows the diagram for the electron energy versus momentum for direct bandgap semiconductor and illustrate the process of recombination between the conduction electrons and holes with the emission of a photon. So what we observed that energy maximum in the valence band and energy minimum at the conduction band occur at the almost same value of the crystal momentum, and this is the case of direct bandgap semiconductor. So thus, when electron-hole recombinations takes place, the momentum of both type of carrier remains the same, and the energy which represent the band gap energy may emit as a light, right? So when the recombinations of electron-hole take place, when the recombination, look at this, when the recombination of electron and hole take place here, the recombination, then the photon is emitted from there. There is a emission of photon. So when one electron, one hole recombine together to give one photon, and the energy of the photon is equal to the energy gap. This is the energy gap. This is the energy gap. So this energy gap is equal to the energy of the photon that is emit from there, and electron and photon is emit there because of the recombination of electron and hole, right? So every photon have the energy Eg, which is the band gap energy. This is the energy gap, right? Same in the case of this. So some of the direct bandgap semiconductors are gallium arsenide and indium arsenide, and gallium phosphide is indirect bandgap semiconductor, right? So the bandgap energy Eg for gallium arsenide and gallium antimonide are 1.43 and 0.73 electron volt respectively. So these are the energy bandgap, and these energies are the energy of the photon as well. So there are some points that I discuss as far as indirect bandgap semiconductor are concerned. So indirect bandgap in indirect bandgap semiconductor, the energy maximum in the valence band and energy minimum in the conduction band occur at different value of momentum that we already discussed and seen in the previous slides. So in this case, when an electron hole recombinations, the electron must lose some momentum so that it has same momentum corresponding to the energy maximum of the valence band. So the process of recombination in an indirect semiconductor is comparatively slow. This is the reason why we not use for this indirect bandgap semiconductor, because the process of recombination in an indirect semiconductor is comparatively slow, and recombination lifetime is of order of 10 to the minus 2 to 10 to the minus 3 second, which is much larger than indirect bandgap semiconductor, which is 10 to the minus 8 to 10 to the minus 10 second, right? Recombination time lifetime is that the time that the what is recombination lifetime of a carrier? The recombination lifetime of carrier is a time to recombine. So we prefer a direct bandgap semiconductor instead of indirect bandgap semiconductor because the recombination lifetime is more in the case of indirect rather than direct one. So I once again repeat that what is actually there is a connectivity issues there. There is some disconnection. What is the carrier lifetime? The carrier lifetime is that time for which the carriers recombine together to give one photon, right? Or number of photons. So the carrier lifetime is more in this indirect semiconductor rather than direct semiconductor. So that's why we prefer a direct band gap semiconductor. In direct band gap semiconductor, we get quick emission of light. That's why we prefer that. As far as spontaneous emission or electroluminescence is concerned, the energy released by an electron-hole pair recombination is approximately equal to the band gap energy Eg of semiconductor. We already discussed that point. The excess of population of minority carriers is reduced by the electron-hole recombination. As the electron-hole recombine together, their density is to be decreased. These recombination may be either radiative and non-radiative. Radiative recombination are the recombination that give you a light, that give you a photon, and non-radiative recombination are the recombination that give you a heat rather than photon. So what we need radiative recombination, right? So this type of emission of light within the diode structure is referred to as electroluminescence. So emission of light within the diode structure is referred as electroluminescence. So in case of non-radiative recombination, the energy is dissipated in the form of heat, and this is not to be desired. So in the spontaneous emission, the energy is released with the production of photon, and the wavelength of emitted light or emitted photon is given by lambda. Lambda is the wavelength of photon, and which is equal to 1.24 upon Eg. What is Eg? Eg is the band gap energy of the material that we used in the manufacturing of this LED. So in this way, we also define what is internal quantum efficiency. It is defined as the ratio of the number of photon generated upon number of electron injected, or you may say number of pairs recombined together. So it is also defined as the ratio of radiative recombination to the total recombination. For example, if the total recombination is 100, and out of 100 only 40 are give you a photon. So 40 are radiative recombination, right? So optical power produced in LED is directly proportional to drive current. Obviously, So the what is the input of the LED? Depending on the amount of current at the LED, which is the input, we get the output. More is the current at the input, more is the power at the output. So optical power produced in LED is directly proportional to the drive current. Thank you very much.